Hello everyone and welcome back. Today we'll be starting off with understanding TensorFlow record. So, when you're using TFDS, your data is downloaded and cached to disk so that you don't need to download it each time you use it. TFDS uses TFRecord format for caching. So usually when we use TensorFlow dataset, what happens is that you download data once, then it is cached in the disk, and whenever you need that data, it gets back to your original location. You can get back the data from disk and use it in the training or so. But TFDS uses TFRecord format for caching. So how does this whole thing work? Let's understand. If you watch closely as it's downloaded the data, you'll see this. So in the next figure, we'll see what kind of data gets downloaded and shows that how CNN underscore Daily Mail dataset is downloaded, shuffled and returned to TF-record file. So let's just see that how this data gets downloaded. So you can see in figure 4-1 that CNN underscore Daily Mail dataset has been downloaded as a TF record file. So you can see TensorFlow underscore datasets slash CNN Daily Mail slash plain text, and in the last you can see train.tfrecord, means it's a TF record file. This is the preferred format in TensorFlow for storing and retrieving large amounts of data. It's very simple file structure, read sequentially for better performance. On disk, the file is pretty straightforward, with each record consisting of an integer indicating the length of the record, a cyclic redundancy check of that, a byte array of the data, and a CRC of that byte array. So what does a file on the disk, what does a record represents? So a record consists of an integer that indicates the length of that record, right? The second thing is a cyclic redundancy check called the CRC of that record, a byte of array of that data, array of that data after the CRC, and finally a CRC for the byte array. The records are concatenated into file. So these records are concatenated or joined together into a file and sharded in the case of the large data set. So for example, let's see that CNN underscore Daily Mail structure this looks like. So you can see that in figure 4-2, this is the whole structure of TF record and how it is inspecting the TF records for CNN underscore Daily Mail and how it's actually stored in TensorFlow datasets, right? So next it says that to take a look at a similar example or simpler example, download MNIST dataset. So we all know how to download MNIST dataset with TensorFlow datasets using tfds.load. Then within the info, you'll see that its features are stored like this. So the features are stored in form of a feature dictionary, and you can see clearly how these features are stored there in the form of a dictionary, right? Similar to CNN and dash Daily Mail example, the file is downloaded to root TensorFlow datasets slash MNIST version files. So the files are downloaded in the file structure only. You can load the raw records as a TF-record dataset like this. How we can load these raw records? So first we know how to load dataset using TFDS. Now we are knowing how to load a data from TF-record as a raw file. So you give the file name first like this. So it's basically the path where the raw data is hiding. Then you get the raw data, you upload it using that file name only using TF-record dataset, and finally you check what kind of data you've got using take of 1. Note that your file name location may be different depending on your operating system. So as we have already seen this one, let's skip it. This will print out the raw contents of the record like this. So when you print dot take of 1, so this will show how this whole raw data is appearing in your files, right? Next, it's a very long string containing the details of record along with checksums, etc. But if we already know the features, we can create a feature description. So if you already know the features, we are creating a feature description here. So we already know that it has image and it has labels, which where the image is a string of where is a string of data type is a string and label has a data type of integers, right? So then we have a parse input function, parse function, and we are just using tf.example proto using the dictionary above. So what does this whole thing is doing is the output of this is little friendlier. First of all, you can see that image is a tensor and contains a PNG. So we all know that image is PNG is a format of an image, right? PNG is compressed image format with a header defined by IHDR, that's short for header, HDR is short for header, that's I is for image maybe, and then and the image data between IDAT and IEND. So DAT is for data, I is for image, I end is image end. If you look closely, you can see them in the byte. So let me just show you where you can actually see all these things is here. So you can see I date means the data stream is starting here, and before that it is like a it's like a header which tells about what kind of data is coming next and what's the location and everything. So every basic information about the data comes in the header only, and then the basic data raw pixels comes after IDAT. Here you can see that, and once the data is complete, and you will get IEND means this is the end of the data stream, right? So anything coming after that is no value related to the data, that raw input that you need. The only text between I start and the I end is only the data. Sorry, I dat and I end is the only required data. At this point, you can read the raw TF record and decode it as a PNG using a PNG decoder library like below. So you can read these raw TF record using a PNG decoder library like a below. So at this point, you can read the raw TF record and decode it as a PNG using PNG decoder like a library called below, right? The ETL process for managing data in TensorFlow. So what is actually ETL and what's the full form? Let's understand this. So ETL is a core pattern that TensorFlow uses for training regardless of scale. We've been exploring small scale single computer model building in this book, but the same technology can be used on large scale training across multiple machines with massive data sets. So, what is the ETL? So, ETL stands for extract, transform, and load. Extract phase of ETL process is when the raw data is loaded from wherever it is stored and prepared in a way that it can be transformed. So, extract phase is basically extracting the data from wherever it is stored. The transform phase of that ETL is actually a phase where the data is manipulated. So all those augmentations that we do, image augmentation and mapping features, that is actually transformation phase. Then we have the load phase. What happens in load phase is that we load the data that we have extracted and transformed to our neural network for training, right? So let's just consider a whole example and we know where the extraction is happening, where the transformation or where the loading is happening, right? So we import our basic imports as usual and we have already written this code. So you can see the model definition starts from model dot sequential and writing all these layers, and finally ends with the model dot compile. Then the extraction phase is when you extract the data, when you use tfds.load. That's the extraction phase and it ends there only. Finally, the transformation phase starts with augment images function where you apply the image augmentation, and ends with validation batches and all the augmented data that you have accumulated. Finally, the load phase starts with model.fit and ends there only, because that's the final load phase. You're loading the data and you're fitting it on the model, right? So I hope this ETL logic is clear. Using this can make your data pipeline less susceptible to changes in the data and the underlying schema. When you use CFDS to extract data, the same underlying structure is used regardless of whether the data is small enough to fit in memory or so large it cannot be contained even on a simple machine. The TF.data APIs for transformation are also consistent, so you can use similar ones regardless of underlying data source. And of course, once it's transformed, the process of loading the data is also consistent whether you are training on a single CPU, a GPU, or cluster of GPUs, or even pods of TPUs. So how this loading and training takes place, let's have a look at this, and it's a very interesting thing to understand actually. So how we optimize the load phase. Let's take a closer look at ETL load process when training a model. We can consider the extraction transformation of data to be possible on any processor including a CPU. In fact, the code used in these phases is to perform tasks like downloading data, unzipping it, and going through it record by record, and processing them is not what GPUs or TPUs are built for. So seriously speaking, that GPUs and TPUs are made for training purposes and are also used for training purposes only. Their purpose is not to download, zip, unzip the data and just store it in the records. That is not what GPUs and TPUs do. For that, only CPUs are mandatory and they're required. So when it comes to training, however, you can get great benefits from GPU or TPU, so it makes sense to use one for this phase if possible. Thus, in situation where GPU or TPU is available, like it's available in Google Colab, you should ideally split the workload between CPU and GPU or TPU, with extraction and transformation phase taking on CPU and load taking phase on the GPU or TPU, right? So assuming you're working with a large data set, so it's so large that you have to prepare the data in batches, you'll end up with situation like that shown in figure 4.3. While the first batch is being prepared, the GPU or TPU is idle. When that batch is ready and it can be sent for GPU to TPU for training, now the CPU is idle and the training is done. When it can start preparing the next batch. So how we actually optimize this is I show you. Let's see figure 4-3. What is happening here is, when CPU is preparing one, the TPU and GPU are idle. But when GPU and TPU are training one, the CPU is idle. Again, when CPU is preparing two, GPU and TPU are again idle. So one is working, the other is idle, or the other is working, first one is idle. So that was the thing. But a logical solution to this problem is parallelizing whole thing, the preparing and training side by side. And this is called pipelining. So what we do is, while CPU is preparing one, GPU and TPU are still idle. But when GPU and TPU are training, CPU can prepare the next lot or the next batch. While CPU prepares the first batch, GPU and TPU again has nothing to work on, so it's idle. When the first batch is done, GPU and TPU can start training. But in parallel with this, CPU will prepare the second batch. Of course, the time it takes to train batch n-1 and prepare batch n won't always be same. So there will always be time when there will be some idle time for the GPU. But as fast as we can do is, we can minimize the idle time to minimum, but it won't be always the time that the training batch is n-1 and the batch that you are providing next is n. So it won't be always possible that there is no idle time. If it's slower, you'll have periods of idle time on CPU as well. Choosing the correct batch size can help you optimize here, And as GPU or TPU time is likely more expensive, so we want to reduce their idle time as much as possible. You probably noticed when we moved from simple data sets like Fashion Amnist in Keras to using TFDS versions that you had to batch them before you train them, right? We have already seen that we'll have to batch these data sets. This is why the pipelining model is in place, so that regardless of how large the data set is, you'll continue to use consistent patterns for ETL on it. So that's why we also do batching, because we don't want idle time for our CPUs as well as GPUs. Next, parallelizing ETL to improve training performance. TensorFlow gives you all the APIs you need to parallelize the extract and transform process. So let's explore the cats versus dogs dataset using TFRecord structure. So first, you already know how to load the cats and dogs dataset. If you want to use the underlying TF records, you'll need to access the raw files that were downloaded. So it's a very large data set, so you can just go ahead and use the load dataset version. You can create a list of these files and use tf.data.datasets.list files to load them. So you can just load these whole file. To load these whole file, you can just list files. Once you have the files, they can be loaded into datasets using files.interleave like this. So use interleave files.interleave. So you can just download the dataset download the files into a dataset, right? There are a few new concepts here, so let's take a moment to explore them. So what's happening here is, when I have train underscore datasets, I'm using interleave to just load all the raw data I have into a dataset. Then I'm using tf.record dataset for the same, and I'm providing a cycle length of 4 as well as number of parallel calls to auto tune. So we are now gonna understand what is cycle length and what is number of parallel calls means here. So the cycle length parameter specifies the number of input elements that are processed concurrently. So what happens is, the cycle length here equals 4 means that there will be 4 elements that are processed simultaneously. Next, this cycle length of 4 is indicating that this process will be handling 4 records at a time. So if you don't specify this value, then it will be derived from the number of available CPU cores that you have. The number of parallel calls parameter then, when set, will specify the number of parallel calls to be executed. And tf.data.experimental equals dot auto tune is also done here, so it will make your code more portable, because the value set dynamically based on the number of available CPUs. So if you don't know the number of available CPU cores, then use auto tune and it will tell you the number of cores that you have presently that can work for you. For example, if the number of parallel calls is set to 6 and after auto tuning the cycle length is 4, you will have 6 separate threads, each loading 4 records at a time. The extract process is parallelized as well. So let's explore parallelizing and transformation of the data. While you create the mapping function that loads the raw records and convert it into usable content, for example, decoding a JPEG image into an image buffer. So as you can see in the code, what we are doing is, we are using image augmentation function or TFRecord read function, where we have given the feature description, we have given the example, serialized example and feature description, and we have applied all the image augmentations that we are using here. So we're resizing it to 300, 300. We are dividing by 255 for normalization, and finally casting it as a tf.float, where we are actually decoding a JPEG image and we are converting it into an image buffer. As you can see, this is a typical mapping function without any specific work done to make it work in parallel. That will be done when we call the mapping function. So when we call the mapping function, it is doing nothing. It is just it won't make it work parallel. How it will be done is, here we are using this code. So what is happening here? We are understanding the number of cores that we have, multiprocessing dot cpu underscore count. So we'll print the number of cores that we have. Then train underscore dataset equals train dot underscore dataset dot map. So we are calling read TF records and passing the number of cores that we have, and finally we'll cache that data that we get. First, if we don't want to auto-tune, you can use multiprocessing library to get the count of your CPUs. So if you don't want to use auto-tune, you just get the count of the CPUs that you have. Then when you call the mapping function, you just pass this as the number of parallel calls that you want to make. So instead of you using auto-tune, you can use this function instead, that is multiprocessing. The cache method will cache the dataset in memory. If you have a lot of RAM available, this is really useful to speed it up. Trying this in Colab will likely crash your VM due to the dataset not fitting the RAM. So it actually happened with me when I tried this whole code on my Colab, and it actually crashed because there was no RAM that could fit my data. So it crashed after one epoch only. After that, if available, the Colab infrastructure will give you a new higher RAM machine. So you can just buy it for Colab Pro or something. Loading and training can also be parallelized, as well as shuffling and batching of the data. You can prefetch based on the number of CPU cores that are available. Here's the code. And here's the code. Train underscore dataset. We just shuffle the training dataset and we'll batch it for batch of 32. So this whole batch goes with 4 threads and number of cores that we have, right? Next, we use dataset.prefetch that just fetches the data as we have already seen. So it fetches the data in CPU as the GPU or TPU is training your model, right? Once the training is set or is all parallelized, then you can just train your model like before. So it actually says that the author also says that it actually reduced the number of training time to 40 seconds per epoch as opposed to 75 seconds that was before this. So it actually decreases your number of the time it takes to train an epoch. Summary is that this chapter introduces you to TensorFlow datasets, a library that gives you access to a huge range of datasets, from small learning ones to a full-scale dataset used in research. You saw how they can be used in a common API and a common format to help reduce the amount of code that you have to write to get access to data. You also saw how to use ETL process, which is at heart of the design of TFDS, and in particular, we explored parallelizing, the extraction, transformation, and loading of the data to improve training performance. Next, you'll take what you've learned and start applying it to natural language processing problems. So in next chapter 5, we'll be starting with Introduction to Natural Language Processing, or NLP. And meanwhile, you can go ahead, try this code. It has nothing much to do, but make sure that you don't use the cats and dogs function in your VM. It might crash because it crashed for me too. But all the code for chapter 4 is available in our GitHub, and the link would be in the description. Do check it out, and if you have any problems or queries, do comment us in the comment section. And thank you for joining in, and I'll see you in the next chapter. Thank you.